Okay, this is the first of what's going to be many videos going over the notes from sections 2.2, limit of a function and limit laws, and 2.4, one-sided limits. I like to do both these sections at the same time. In your homework, I have both sections all in the same homework assignment. But if you're a textbook reader, you will need to read both sections separately. And then we'll come to 2.3 after this. So starting this out, we've got a function here, f of x equals x squared minus 9 over x minus 3. Find f of 3. So remember that functional notation means that we just replace the x with 3, and we see what we get. And in this case, we get 0 over 0, which is undefined. It really is very important to remember that division by 0 when we're doing functional limits is always undefined. A 0 in the denominator when we're doing functional values is undefined. So when x is exactly 3, all we can say about this function is its functional value is undefined. But let's investigate what's happening to this function as we get closer to 3. Now there are two ways we can get closer to 3. We can use numbers bigger than 3, which we say x approaches 3 from the right, or we can use numbers less than 3, or x approaches 3 from the left. Notice less and left both L's. So I'm going to take these numbers, plug into my function up there, see what we get. So when you plug 3.1 into the function x squared minus 9 over x minus 3, you're going to get 6.1. Then 6.01, 6.001, 6.001. Don't read anything into that 3.1 gave me 6.1. 3.01 gave me 6.01. That's just coincidence. And so what this chart implies, and when we notice that we're getting closer and closer to 6, this chart implies this right down here, that the limit as x approaches 3 from the right of f of x equals 6. That's an example of a right limit. And again, don't read anything in here, numbers bigger than 3, numbers bigger than 6. That's just this particular problem. Over here on the left, we have numbers less than 3, so this is approaching 3 from the left. Plug in, and I get 5.9, 5.99, 5.999, 5.99999. Again, all we did here was plug into the function x squared minus 9 over x minus 3. Read nothing into that 0.9 went to 0.9. Read nothing into here that these are smaller than 3, these are smaller than 6. That's all just coincidence. What we do want to observe is that as we got closer and closer to 3, but on the left this time, we still got closer and closer to 6. And so we say here that this chart implies the limit as x goes to 3 from the left of f of x equals 6. The right limit, the left limit. And in this particular case, they both happen to be 6. Now that's a left limit and right limit. They're also two-sided limits. And here's an important fact about two-sided limits that you should memorize, which is a two-sided limit exists if and only if both the left and right limits exist and are equal to each other. In this case, all the limits have the same value. A two-sided limit exists if and only if left and right limits exist and are equal to each other. So using that fact, we can see that from the previous charts, we had a right limit of 6, a left limit of 6, and so since the left and right were both 6, the two-sided limit has to be 6. A two-sided limit exists if and only if the left and right limits exist and are equal to each other. Then down below here, I have the graph of the function. So there's the graph of x squared minus 9 divided by the quantity x minus 3. This open circle right here, and we have it right here, the open circle at the point 3,6 corresponds to a missing point and the fact that f of 3 is undefined. Remember, when a functional value is undefined, you're not going to have a y-coordinate on the graph at that point. And so because we're undefined at 3, x equals 3, there's not going to be a y-coordinate. And further notice, as I'm on the left of 3, my y-coordinates get closer and closer to 6, and when I'm on the right of 3, and as I go closer and closer and closer to 3, right down here, 3 right down here, and my fingers come closer and closer to 3, my y-coordinate is closer and closer to 6. That limit answers are going to be your y-coordinates. That as you come closer and closer and closer to the x value in question, your graph will have y values coming closer and closer and closer to the y-coordinate. Now, in general, the limit as x approaches a of f of x equals L means that as x values come closer and closer to the number a, the values of f of x come closer and closer to the number L. So I'm going to switch up the graph a little bit. So here was my original graph. The functional value, which was that circle that open circle right there, which just represents a single missing point. My functional value was undefined. My limit was 6. So now I'm going to change up the function just a little bit. Go to a piecewise defined function where my function is equal to x squared minus 9 over x minus 3 if x is not equal to 3. And it's equal to 6 if x equals 3. And so here's my graph here. And the difference between these two graphs is I've merely kind of filled in that hole. That I've now specifically defined the function to be 6 when x equals 3. And so here, f of 3 equals 6, but the limit is still 6. So I changed the function, but the limit's still 6. And the limit's still 6 because when I come closer and closer and closer, my y value is still going to be closer and closer to 6. Here's x equals 3, go up and over, and my y coordinate is going to be closer and closer to 6. And so what I would ask a classroom full of students, and I'm lecturing in an empty classroom, what I'd ask is, why is the limit still 6? I changed the function. I changed that f of 3 is now 6. Instead of f of 3 being undefined, f of 3 is now 6. Why didn't I change the function, change the limit? And the reason why I didn't change the limit is limits are about close to. I didn't change what was happening close to 3. All I changed was what was happening exactly at 3, and so that's why the functional value changed. The functional value changed to 6. F of 3 is 6, but the limit, which is close to, did not change. Let's change up the function again. So this time, instead of, I still got the x squared minus 9 over x minus 3 if x is not equal to 3. This time I have it equal to 2 if x equals 3. And so when we see the graph there, and so the difference in the graph this time, instead of the hole being filled in up there, the hole is down here. That this 3, 2 corresponds to f of x equals 2 if x equals 3, or f of 3 equals 2. And remember, when you're doing functional values in graphs, x coordinates go in, y coordinates come out. And so the question I would ask if there's a classroom full of people here is, why is the limit still 6? So here f of 3 is 2, but the limit is still 6, and it's the same reason. The limit didn't change because we did not change what was happening close to x equal 3. Limits are about close to. And in none of these examples did I change what was happening close to 3. I only changed each time what was happening exactly at 3. So each time the functional value, which is exact, changed, but the limit didn't. And so here, the point to these 3 previous examples is that limits and functional values do not necessarily have any relationship. Just because a limit is known says nothing about the functional value, and just because a functional value is known says nothing about the limit. Limits are about close to, functional values are about exactly equal. And that's where we'll end this first video.